Hello guys, welcome back to another video on my channel. In the past couple of videos that actually filled up the Laplace Transform playlist, we talked about the basics of Laplace transforming a function and then inverting the Laplace transform, and the latter was a little more involved than the other bits. For Fourier transforms, it's just a contour when you're inverting. Sorry, it's just an integral when you're inverting. Here we had a contour. We gave some examples in the past and hope you sort of see the big picture of how to do these, how to approach these questions. In this video, I'm going to talk about some properties, some really useful properties of the Laplace transform. So let's get started. So I think what I should do first is review some of the properties of the Fourier transform so that we at least know what to expect, because the Laplace transform is a generalization of the Fourier transform. So I have a function of t. This double-sided arrow is the Fourier transform arrow. So this gives me f of omega. That's the Fourier transform of some function f of t. If you have the same function but shifted by a time t naught, then the Fourier transform of that, and we proved this in that video. You should check that out if you don't know or it seems a little foreign to you. This is f, but I'm underlining it because this could be complex. This is not an e, this is an f with an underline on it. And then the derivative of f of t was I omega f of omega. And we also proved these things. F of t convolved with g of t gave us square root 2 pi Fourier transform of f times Fourier transform of g, and then we had a product giving us a convolution of Fourier transforms. So these were the things we had. We can try to sort of find analogs for the Laplace transform. I mean, they should exist in theory. If you go on building up the Fourier transform or the Laplace transform from the modified Fourier transform, if you have a function, all you need to know that for negative t, this is 0. This is one assumption we will make. These are the functions we're going to work with. So f of t minus t naught, what's the Laplace transform of this going to be? Maybe just have an arrow like before. Integral from 0 to infinity e. We have a dt, e to the negative st, where s is complex, f of t minus t naught. Do a nice change of variables. So we have something that's going from so the variables t minus t naught, so minus t naught to infinity, d alpha e to the minus s alpha plus t naught, f of alpha. Now just moving ahead, we can sort of extract one of those terms out, ones that don't depend on alpha. And then this is just the Fourier transform, sorry, the Laplace transform of of f, which I will denote as capital F of s. Just one point I want to make, I jumped from this to that, is because f of alpha for alpha less than 0 is 0. So this essentially just becomes, because if we set t naught to be a positive constant, then the 0 to negative t naught bit is always 0 because of this condition here. That's why we wanted this to start with. So this just becomes integral from 0 to infinity. That's the finite, the non-zero part. And then that just gives us the Laplace transform. Now, what about derivatives? We have, just write it down. The trick is the same as before. We want to do some integration by parts here. So if I integrate the derivative part, I have this evaluated 0 to infinity plus s when I differentiate the exponential dt e to the negative st f of t. Now one thing to note is that this guy will sort of decay to 0 at infinity. At 0, exponential is 1, but we still have an f of 0 that we aren't guaranteed it will go to 0. The infinity bit went to 0 because f cannot really grow more than this exponential bit, otherwise the Laplace transform does not exist. And then this is just the Laplace transform of f. So this is the formula. Notice the differences we have. If you want to take analogs, we had I omega is just s, right? But we also have this f of 0. That's because we're integrating from 0 to infinity, not from minus infinity to infinity, in which case we had at least some hope of that dying down to 0. But there's no such guarantee. And this kind of makes sense because if the Laplace transform is a generalization, we want to be more general with the endpoints. So we have the function evaluated at 0. Nice, this is nice. We can generalize this and we get, for an nth derivative, and we get like s to the n f of s and lower order derivatives of f evaluated at 0. I won't write it down, you can check it. It's not really that interesting. You just repeat this generalize, it's not hard. And I believe there should be, there should be a negative here because there is the lower bound we're evaluating it. Okay, so assuming we have f of t, that's, satisfies this, it's 0 for negative t. A similar function, say g of t, which have corresponding Laplace transform f of s and g of s. What we want to do is sort of find a formula like this. We got this, we got that, we got this, an analog for that at least. We want to find this. So let's try convolving the Laplace transform of f of t convolved with g of t. So let's see what that is. Before moving on with the gritty math, h of t, which is, I'm going to define as whatever's inside, is the convolution of these guys, with the integral for which I'm not writing the upper and lower bounds, but then minus infinity to infinity more generally. So the integrand is looking like this. So if you have f of t, that's something like this, and g of t, that's like that. Then the convolution, at least the integrand, f of tau is essentially going to be the same things, but instead of a time or t-axis, we have a tau axis. Now the g of t minus tau is going to look something like this. Maybe I should just draw it somewhere else. My bad. So assuming this is your t, because we're working on a tau axis, t is a constant. Yeah, it's going to be something like this. It's like flipped around this guy, and then 0 everywhere else. So what we do when we integrate is that we sort of move these guys within each other. So we sort of overlay this and that, and then sort of change the tau value so that there's gonna be a point where these guys overlap, and that's when the integral has its maximum. Everywhere else, when these guys are sort of not in sync, it will be 0 because this, and then there's a 0 here, so that multiplies to give you 0. This is negative here, there's a 0 there, so it multiplies to give you 0. It's only non-zero when this overlaps with that, when we've sort of progressed forward in our integration. So that's the intuitive picture. It's time to do the nitty-gritty math. Okay, moving on. H of t was f of t convolved with g of t, which I'm going to write the transform of this guy to be h of s. H of s was integral from minus infinity to infinity. I'm doing the full convolution definition for this, or dt. Or maybe let me just rewrite a bunch of things here. Let's write the Laplace transform definition first. Right? And then we can substitute what h of t is. It's this, but then we also are sort of given that h of t is 0 for less than 0, so we can sort of make this an integral from minus infinity to infinity. This will sort of help us generalize later when we extend the Laplace transform a little more. That's right, there's more extensions for this thing. H of t is the convolution. I'm writing the formula for the convolution of f and g. Is that? Now, what I want to do, I'm going to substitute for each of these guys. For f and g. So this is just the inversion of capital F of s and then we can do the same for g. So remember, I have different contours marked for the inversion, because the one for f may not be the one for g because different regions of convergence and all that stuff. Yeah, this one's gonna be a long nested integral. I'm gonna demark this s and s prime separate because they're independent variables with respect to each other, and then a double prime for the one for g. We can sort of use the property from before, the time shift property, to get this. For g. Yeah, there's a prime here. Okay, now what I'm gonna do is I want to just collect a bunch of terms. There should be a 2 pi I also. Connect the 2 pi i's. You have a negative 1 over 4 pi squared integral from minus infinity to infinity. Take the d tau, interchange everything, so that the d tau comes outside. The ds primes as it is, e to the s prime tau, f of s prime. I might not underline it all the time because it's just annoying. There's a lot to write. And we have a g of s double prime. And I think maybe I should use the next line. This is all in one line, but and then the t integral, e to the minus s t e to the s double prime t. Now what I want to do, I want to sort of find a way to get a Dirac delta out of all of this. That will really help us break everything down easily. So here's what I'm going to do. I'm going to visualize a bunch of things. The s double prime plane, that's sort of the region of convergence for g. We don't really know what the function really is. Let's do some guessing here. So say this is the line beyond which you sort of cannot move your contour of integration, your Bromwich contour. So you can't exceed this line, which means, this is sort of accounting for what if the Fourier transform does not exist. What if we can't really place LG onto the imaginary axis? This accounts for all of that. You can move it anywhere till infinity on the right side, but you can't really move it beyond this on the left side. So region of convergence of G is literally from this line till infinity. So S double prime, or whatever we're going to use for integration, is going to be a point on this line. Now look at the S plane, the regular S plane that defines the final output for whatever we have. Well, that we don't really know the characteristics of the region of convergence. Let's just be a little more free with that. Say here's the point S for which we're doing all of this calculation. An arbitrary point in the S plane. So what I want to do here is these guys, S and S double prime, are complex. So what I want to do is I want to move this contour such that it coincides with the real part of this guy. So real part of this guy, say S sub R. This has a real part S sub R double prime, plus every point on this contour has an imaginary part as well. Well, it should. I hope it does. Same thing with here. You can break S as S real plus I S imaginary. So what I want to do, I want to move this guy, because as I said, I can move this anywhere from this line to whatever point. So I want to move it such that this line coincides with this line, the real line for S here. What that allows me to do, allows me to set SR double prime to SR prime. So S double prime is just SR plus I SI double prime. You might not see why this is so useful, but let's just look at this integral. We have this dt e to the t. I'm going to decompose everything down. So I have S real for this plus I. So whatever's positive, S double prime is positive. S double prime is S real plus I S imaginary double prime, because we placed we sort of made the real parts coincide, minus S real, that's this guy, minus I S I imaginary. That's it. The advantage of this is this goes away, and this is also a way of ensuring convergence. If the if the real part or the magnitude of this argument, this integrand, did not go away, then this would have blown up. Look at the convergence in terms of real numbers. As long as it's phases, it's fine, because then we can just produce a Dirac delta out of all this from the Fourier transform definition of the Dirac delta, which turns out is really, really useful. You need imaginary quantities in the argument of the exponential to make it in a Dirac delta function. So you have delta Si double prime minus Si, and the 2 pi for normalization reasons. So we just plug that in here, everything. So the 2 pi and this 4 pi squared will like sort of take one of them away. We have this. Well, d tau does not change. Everything else is literally unchanged. Just get rid of the t integral. And we have g of s double prime delta Si double prime minus Si. Okay, now what I want to do is I want to sort of integrate. I want to consider the integral for Lg. So I'll have to parameterize. So how will I parameterize? Well, S double prime is, well, we know S real plus Si double prime. The real part's fixed on Lg. So ds double prime is just I dsi double prime, and imaginary part going from minus infinity to infinity. So with this substitution in place, these things are hard, or I have to be a little more careful compared to the Fourier transform convolution. That was just easy. Everything was real. Here we have to work with contours, fix everything up. Minus infinity to infinity. We have an I from this integration constant, integration variable rather, with e to the minus s real plus s imaginary double prime of tau g of s real psi double prime. But what this Dirac delta does is that it changes, or let me just write it down, it's probably better for everyone. So I have something like this. So now I can contract over the index Dirac delta property. Si double prime becomes an Si, and we get rid of the integral. The I sort of, you can take it out. See, this is good. We have to break every integral down and reduce it down, get rid of the integral, and reduce the number of variables where we're at it. Because notice now what's happening here is that we have e to the double prime became just, you probably need an I here. I forgot that. The double prime became a no prime, so SR plus I S sub I. That's just what S is, right? That's just what S is. So let's just write it minus S tau, I believe, yes. And same thing here. We have G of S because double prime becomes no prime, and then there's this S. Now, what we can do is repeat the process that we did to generate a delta. So again, interchange integrals. We have to consider the tau integral. So tau integral is d tau e to the tau s prime minus s. So now for this, I have to sort of repeat this argument again. So let me draw an S prime plane. and the S plane. So S prime plane, we don't know what the characteristics of f of t are, but let's just assume there's some line which you cannot exceed, that and from which to infinity is the region of convergence of, you guessed, f. That's the S prime plane. Maybe have like a arbitrary line here, placed in the region of convergence, the line of inversion. The S plane is sort of unchanged before. Real, imaginary, some arbitrary point, that's S. S sub r plus I S sub I. Any point here, S prime is SR prime plus I SI prime. From the same argument as before, you can see a convergence of this integral, or just convenience. We can shift this such that the real part of S prime is equal to the real part of S. So S prime, after shifting this LF such that the real parts coincide now for both the planes, S prime is just SR plus I SI. We can plug everything back into what we had before. So I believe we had this, that, and this. So d tau as it is, just decompose everything, e to the tau. S prime is, as I said, SR plus I SI. I forgot the prime, my bad. Prime minus S, and S is SR minus I SI. This cancels, which is nice. We can regenerate a Dirac delta here. Just this integral just becomes the Dirac delta. This extra 2 pi factor, so that cancels with the denominator. We have minus I. I have this S prime G of S, Dirac delta SI prime minus SI. And now if I parameterize along this path, S prime is SR plus I SI prime, ds prime is I dsi prime. Along the path we're going to go from minus infinity to infinity. That's the imaginary part, extinct. We have I dsi prime, f of SR plus I SI prime, G of S, that's like unchanged, so keep that intact. Delta SI prime minus SI. That will change this prime to an SI. This will become the 1, minus I and I become 1. So maybe I can just skip all these steps, because notice what's happening. The Dirac delta here will change the I SI prime to SI. So SR plus ISI is S, so f of S. And this was independent of the integration. I should have taken it out way before. So it's that. So here's, we really get a product. So here's the formula. After all of this big mess, Laplace transform of f of t convolved with g of t is the product of Laplace transforms. That's really powerful, a really nice formula. Okay, moving on to the next property. Okay, given that we know what the Laplace transform for convolution is, this will go a lot faster, the product. So define h of t as f of t times g of t. So we have a product here. The same property as that, this is 0 for negative t. That holds, that's like the unsaid thing here. So I want h of s Laplace transform of f of t and g of t. So just by definition, I can take a minus infinity because the negative bit is 0. That doesn't really matter. Fair. Now I'm just gonna plug in the definition for the inverses for these guys. So 1 over 2 pi I squared, as before, is 1 over negative 1 over 4 pi squared. So that factors something that's always there, dt e to the minus st. So that's the inversion for f. There's no funny prefactors in the or arguments in the exponential, just straight up. And then do the same for g. Double prime and single prime, because they're independent. This is important. People mess this up. It's a common place to make mistakes. But the t is the same. Yeah, I should not have put a prime here. Yeah, my bad. As long as you don't make this mistake, it's all fine. Okay, so now what do we do? Well, as before, just group some terms. So we'll have to group the t integral terms, usually the exponentials, because those will generate the Dirac delta under the appropriate condition that we will restrict. So, having these conditions in place sort of also tells us what the region of convergence will be for h of t, capital H of s rather. So before it was sort of move all of them here, it's going to be a little more tricky. So the real part of the s prime, real part of s double prime minus real part of s, they should be 0, because we don't really want a magnitude on this guy. We just want a phase. So ensuring this means that the magnitude doesn't matter here. It's always going to be equal to 0. This means that we're going to shift the line of inversion LF and LG such that on we're going to move them onto some real part, such that when you add them up, that should equal whatever point you're at on the S plane. So this is a little tricky. I won't draw diagrams, but you can say this is for convergence, and this is the way you can define the convergence. Region of convergence is basically sum of individual regions of convergence. Well, doing that is a relief. I'm going to skip some steps, but it's easy to see that we're going to generate a delta function. The imaginary parts will. The real parts go to 0. The imaginary parts that remain become the definition of the Dirac delta function. So I'm just going to directly write that 2 pi for the prefactor Dirac delta si prime plus si double prime minus si. Now contract over everything, or rather, let's parameterize first. That's probably a better idea. So just parameterize along this imaginary path. So I will have let's see. I have this. So instead of like the real part of double prime, I can just substitute the prime minus this plus double prime. The imaginary part, always keep that intact. So now once we contract over the index, contract to use the property of the Dirac delta, the double prime can be replaced by a single prime minus no prime in the imaginary part. So that becomes so you can contract nicely, and if you notice, you group some terms together, you'll notice this becomes s prime minus s, really the same stuff as before, which I can really rewrite as 1 over 2 pi I integral along LF ds prime f of s g of s prime minus s. And this is sort of the final answer we're looking for. The fun thing is we contracted the Dirac delta, or sort of parameterized the path LG. What if we had parameterized the path LF? Then we would have ended with a final answer like this. So you notice this sort of switched around, the argument switched around, but important thing, unlike the Fourier transform formula for the same, is to pay attention on what contour we're really inverting on. But I can generally write this as convolution of f of s g of s. In this case, this is a more complex version of the convolution, but this is, we can define totally as a convolution. That's why that we have a complex convolution. That's why it matters what contour of inversion we took initially. So, well, this is it. These are all the important properties you really need to know. We will mostly use the derivative property and the time delay, the t minus t naught property for differential equations and applications and Green's functions and stuff. So this is pretty much it. Thanks for watching, guys. Please like, share, and subscribe. Peace out.